feel your love. I just wanna feel your love.
So here's an illustration of the circuit we're going to analyze. We have a 12-volt battery with 4 resistors. R1 is 6 ohms, R2 is 36 ohms, R3 is 12 ohms, R4 is 3 ohms. We want to analyze that circuit, which means we want to know what is the voltage across each resistor, what is the current through each resistor, and what's the current provided to the circuit by the battery. So what we're going to do is boil the circuit down from 4 resistors all the way down to one equivalent resistor. It's equivalent in the sense that the battery will send it that single equivalent resistor the same current that it's sending this for right now. Now, we're not going to go from 4 to 1 in one step. What we do is we go from 4 to 3, 3 to 2, 2 to 1. So we're going to take two resistors in this circuit that are clearly just in series, which each other or just in parallel with each other, and reduce them to a single equivalent resistor. And we'll keep doing that until we're going to a single resistor. Then we get down to single resistor. We can find the current in the whole circuit and then expand the circuit back out from 1 to 2, from 2 to 3, from 3 to 4 resistors. Okay, so a couple things to remember. Resistors are in series when the same current that passes through one resistor goes on to pass through another two resistors, are in parallel when they are directly connected to each other at one end and directly connected to each other at the other end, nothing in between, and then you see the current split, some passing through one resistor through the other, and then that current recombines. Okay, so back to our circuit. Where do we start? Which two resistors should we combine into a single resistor? And what we're going to do is we were going to start with resistors 2 and 3. You should be able to see that those are in parallel if you follow the current from the battery. Some goes down through resistor 1, some goes down the right, and it will split, and that stuff that goes to the right will split. Some will go through R2, some will go through R3, and they'll come back together and go through R4. So those guys are in parallel. In fact, that's the only place to start in this circuit. Note that R1 and R4 are not in parallel with one another, just with one another, because although they were connected together at the lower end, they are not tied together with nothing in between them at the upper end. So this fact that R23 is in between them means they're not strictly in parallel with each other. So we're going to start with our 2, 3 being in parallel. Okay, let's combine those. So we can combine those to something we'll call R23, and we do that with the adding resistors. In parallel equation, we take the inverse. So 1 over 38 ohms plus 1 over 12 ohms. How do you add those? Well, you put them over the same denominator in a common denominator is 36 ohms. So 1 over 12 ohms is the same as 3 over 36 ohms. So we add 1 over 36 and 3 over 36 to get 4 over 36. Remember, that's 1 over R23. So flip that result upside down. R23 is then 36 ohms over 4. In other words, it's 9 ohms. Okay, so now we're here. We have a 6 ohm resistor and 9 ohm resistor. And a 3 ohm resistor, how do we combine them? Again, R1 and R4 are not yet in parallel, which each other because of this R23 that's in between them. So you should be able to see that R23 and R4 are in series. And so we combine those in series, and that just means summing those two resistance. 9 ohms plus 3 ohms is 12 ohms. Okay. So now we have a 6 ohm resistor in parallel with a 12 ohm resistor. Okay, so then we add those together in parallel to boil it down to a single equivalent resistance. And this might be going a little bit too far. It's further than we really need to go, but it's fine. Okay, so we'll do this anyway. So we combine them in parallel. We get 1 over 6 ohms plus 1 over 12 ohms is 212 plus 112, that's 312. If you keep your units there, which is a good rule of thumb to do, then you remember that your units are, you know them. So we have inverse ohms here. So that reminds you to flip the thing upside down. So REQ is 12 ohms over 3, that's 4 ohms, right? So now what we've done is we have foiled out circuit down to a single equivalent resistor of 4 ohms connected to a 12 volt battery, and now it's a piece of cake to find the current. So we simply say we got 12 volts across 4 ohms. We apply Ohm's law. I total from the battery is the battery voltage. That's also the voltage across the 4 ohms resistor divided by the equivalent resistance. 12 volts over 4 ohms is 3 amps. Okay, so there's 3 amps coming out of our battery. Great. So we're through the process. We got to expand the thing back out again. And when we do that, we expand it a pair at a time. We just go in the reverse order to the construction that we did. Okay, so remember what do we have a 4 ohms resistor with 12 volts across it and 3 amps going through it, but that came from a 6 ohm in a 12 ohm resistor. And parallel, so when you expand a single resistor back to the 2 that it came from in parallel, the rule is that the voltage across the 2 is the same as the voltage across the 1. In other words, we have 12 volts on the 4 ohm, we had 12 volts across each of the 6 ohm and the 12 volts ohms, and the current splits. Okay, so here we've got 3 amps or current, and it divides between the 6 and the 12. How do you know how much current goes through each? Well, the voltage is 12 volts across is 6 ohm resistor. Use Ohm's law to get the current of 2 amps. You got 12 volts and 12 ohms on the other one that corresponds to 1 amp. Okay, and make sure you can check the answer right. The 1 amp of 2 amp should add up to the 3 amp. That's come 3 amps. That's coming from the battery, so the 3 amps comes along, splits 2 amps, goes one way, 1 amp goes the other way. Those currents come back together and go back to 3 amps going through the battery. Okay, now, this 12 ohm thing did not exist in the circuit in the first place. It was actually separated 9 ohms and 3 ohms. So we'll expand that back out, and that's in series. So when you do that, the rule is that the current stays the same. So the current and the 12 ohm through the 12 ohm resistor was an amp. So now, when we split it back out into a 9 ohm and 3 ohm resistors, we keep that one at current, and then we can apply Ohm's law to figure out the voltage, and 9 ohms and 1 amp corresponds to 9 volts. 3 ohms in 1 amp corresponds to 3 volts. And you can again check your answer. The sum of those two voltage 9 volts plus 3 volts should add up to the 12 volts that we had across that single 12 ohm resistor. Okay, the very last step, remember, we had 4 resistors to start with. The 9 ohm thing was not really there. It was the combination of a 36 ohm resistor in parallel with a 12 ohm resistor. So we split that back out. The parallel pair it came from, and again, when you do that in parallel, you keep the voltage and you split the current. And so how do you know what the current is? Well, we keep the voltage of 9 volts and 36 ohms when you plug that into Ohm's law. Get your current of 1 quarter of an amp, 0.25 amps, 9 volts and 12 ohms gets you 3 quarters of an half 0.75 amps, so you can check again that those two things should add up to the 1 amp we had going through the 9 ohm resistor, and 0.25 amps and 0.75 amps does indeed add up to 1 amp. Okay, so now we have analyzed that circuit. We know that the current at all points in the circuit. We know the voltage across every one of our resistors in the circuit. So really, we know an awful lot about this circuit. Now, that is the end. We're going to talk about the capacitors in series and parallel, and we're going to go questions that you need to know and work on some problems. So let's say if you have a battery attached to two capacitors in parallel, let's say the two capacitors are parallel to each other, and let's use a 10-volt battery. Let's call the first capacitor C1 and the second one is C2. Let's say the first capacitor has a value of 100 microfarads. The second capacitor has a value of 200 microfarads. What is the equivalent capacitance of this circuit for parallel circuits? The equivalent capacitance is simply the sum of all the capacitors connected in parallel. So it's 100 plus 200, so it's 300 microfarads. And that's all you need to do to find the equivalent capacitance. Now, how much charge is stored in C1? To calculate the charge, Q1 is equal to C1 times V1, so you need to know the voltage across C1 in a parallel circuit. The voltage across every element that's parallel to one another is the same. C1 is connected directly across the battery, so it has a voltage of 10 volts, and the same is true for C2. They will all have the same voltage. So V1 is 10 and V2 is 10, so now we can calculate Q1. So it's going to be C1, which is 100 microfarads, and 100 times 2 minus 6. Micro is 10 to the minus 6, and V1 is just 10. So Q1 is about 0.001 coulombs. That's the unit of electric charge. Now what about C2? What is the charge stored in C2? So we can use this equation. Q2 is equal to C2 times V2. So that's 200 times to the minus 6 times 10 volts, so it's going to store twice the amount of charge compared to C1. So it's 0.002 coulombs. The total charge stored in this network is basically Q1 plus Q2. So it's 0.001 plus 0.002. So it's 0.003 coulombs. You can also find the total charge by taking the equivalent capacitance and multiplying it by the voltage. So 300 times 10 to the minus 6 multiplied by 10 will also give you 0.003. So that's another thing to keep in mind. Now, how can we calculate the energy stored in C1? What is the electric potential energy stored in that capacitor? One equation that you can use is this one. It's 1 half CV squared. So it's 1 half times 100 times 10 to the minus 6. That's the capacitance times the voltage across the capacitor, which is 10. And don't forget to square it. So this is equal to 0.005 joules, which we could say it's about 5 millijoules. Now, what if we have a capacitor circuit in series? Let's use 3 capacitors instead of 2. So the left we have a battery. You can see the two different sides of battery, and let's say the battery's voltage is 50 volts. Let's call this capacitor C1, C2, and C3. Let's say C1 has a capacitance of, let's use large values. Let's say C1 is 2 farads. C2 is going to be 3 farads, and C3 it's going to be 5 farads. Now, typically most capacitors they're in a range of microfarads. Supercapacitors have this much capacitance, but just for the sake of simplicity, we'll use these numbers. What is the equivalent capacitance in this circuit? That's the first you want to look for. A simple way to find the equivalent capacitance in a series circuit is going to be 1 over C1 plus 1 over C2 plus 1 over C3, all raised to the minus 1. So it's 1 over 2 plus 1 over 3 plus 1 over 5, and just type this in exactly the way you see it in your calculator. So the equivalent capacitance is about 0.9677 farads. Now with this information, how can you find a voltage across each of the capacitors? Sometimes, you may need to find the voltage of just one of the capacitors, and then with that you can find how much potential energy is stored in that capacitor. But let's focus on finding the voltage of each. So once you have the equivalent capacitance, the next thing you need to do is calculate the charge. Now there's some differences you need to know between a series and parallel circuit. For capacitors in a series circuit, in the parallel circuit, the voltage across each capacitor is the same. It's equal to the battery's voltage in a series circuit. The voltage across each capacitor will be different if the capacitance is different. Now, in series circuit, the charge stored in each capacitor is the same. In a parallel circuit, the voltage across each capacitor is the same. Make sure you understand that difference. So once we find Q, this Q will be the same as Q1, Q2, Q3. They all equal each other. And this will be very helpful in calculating V1, V2, and V3. So let's find Q. It's equal to the equivalent capacitance times the total voltage, or the voltage of the battery, which is 50 volts. So 0.9677 times 50 times equal to 48.39, and that's a rounded answer. So that's the total charge, which is the charge on each capacitor, which are the same. So now let's find V1. It's going to be Q1 over C1. So take the charge and divide it by the capacitance. Now if you have the microfarads, make sure to add 10 to the minus 6 when dealing with your calculation. In this situation, I just got a divided by 2 since it's in farads. So 48.39 divided by 2 is about 24.2 if we rounded to the nearest 10. So that's the voltage across C1. Now to find the voltage across C2, it's going to be Q2 divided by C2. Q1 and Q2, they both equal to Q. So it's going to be 48.39 divided by 3, and then that is equal to 16.1. Now to find the C3, it's going to be Q3 divided by C3, to find V3. So V3 is going to be 48.39 divided by 5, and that's about 9.7 volts. Now notice that the total voltage is equal to V1 plus V2 plus V3. V1 is 24.2, V2 is 16.1, V3 is 9.7. So if you add these values, you should get 50 volts, which is equal to the voltage of the battery. That's how you know if your answer is correct. It has to agree with one another. The sum of these three values has to equal the battery's voltage. Now let's calculate the potential energy of C2. It's going to be 1/2 CV squared. Now that we have the voltage, we can find the potential energy. So the capacitance is 3 farads. The voltage across it is 16.1, and so this is equal to 388.8 joules. And so that's the end.
Look, see, I remember when I met you as a sophomore. Started out as friends, but I knew that we would want more. Hit your favorite restaurant with your